So I'm going to talk about Wind. It's a research platform for doing research about cloud orchestration and cloud management for distributed heterogeneous clouds. And I'm going in this presentation to tell you what this is, what this platform is, what it can do. And I will also make some comments about how we have implemented this thing. This is a like 4-year work. And I haven't been allowed to present this before. This was done starting 2009, 2010, but for corporate reason we weren't allowed to talk about this, but now I'm allowed to do that. So, first, what was our initial assumption here? Ericsson hadn't been into this area, so we were 10, 15 years behind in cloud. So, what we want to do was something that was interesting for us as well, and that was to try to leverage from the network architecture that we provide, and then having that, how can we take that into the cloud and make something worthwhile for others to use? So doing this, we also wanted to identify all the problems that we see you can find, verify possible solutions, and do that through prototypes. And what we came up with that would something new was the distributed cloud. And the distributed cloud is when you connect lots, hundreds or thousands of data centers together, big and small, to one big cloud where you can have really distributed applications running in a simple manner. So, first, what is a distributed heterogeneous cloud then? Let me talk about. Yeah, it's a cloud where you have big centralized data centers with tens of thousands of servers. And you will have some smaller data centers as well with maybe a couple of hundred data servers. Or really tiny ones, from 1 to 10 servers. And so that is a huge broad variety on the size of each data center. And also, each data center might run different cloud stacks, cloud operating systems, like OpenStack, like CloudStack, or VMware, or something. Or it might even not have a stack at all. We are controlling it directly, the machine, through a hypervisor. So our system has to support all this. So we set up a number of requirements and design goals for this. And as we say, it's a fully heterogeneous environment that we have to support. We thought that all APIs in this should be RESTful. And we should build the system around a set of separate services that you can use all together, or just pick one of them for your solutions. And let application domains drive the requirements on top of this cloud platform. And then our lead words here were to simplify as much as possible doing management and orchestration of clouds, and at the same time automate as much as possible. Make it easy for the tenants to use this. So we came up with an architecture for this. This is slightly simplified, but you can see here we have two. Sorry about that. Wrong button. We have the cloud orchestration domain, and that sits now on top of a cloud execution domain. In the execution domain, we can have different things, as I said, OpenStack, Amazon Web Services, VMware, directly talking to LiveVirt, whatever we find out in the future there. So we should be able to support that. At the same time, we wanted to be able to support whatever API that is convenient for our tenants. So that could be like someone wants to have an use the OpenStack API. We should be able to support that. Or VC3. Or our own that we have developed, Wind API. And now it looks like here that we have sort of an API connector in top and one southbound. But in reality, how you should view this is that each individual service that we have these northbound API and Southbound API that is fully plug-in supported. Okay, what kind of service do we have? Yeah, we have some fundamental service that you would expect, like storage, compute, network, image handling. This is what you basically find in any data center and cloud stack today. We have, of course, for identity, that is important. We have built up around the kernel of other more internal things that is needed to manage and administrate, especially in a distributed one, all the data centers that we have. We have then also a set of what we call intermediate services. This is for handling more automation of things, like automatic scaling of an application. This is, by the way, more for an infrastructure as a service. It provides infrastructure for a cloud. We have a trigger service where you can sort of monitor things that you have, all the resources you have available, monitor that, and trigger if something goes wrong, but also for measuring from different metrics, how is it time for this application to scale out or scale in, add more resources, or remove resources that are not used any longer. As it's a distributed cloud, location will become very important. Where do I have things? Where do I have my resources? And also, we have support for distributed applications. If you, for instance, one such an application could be a distributed video conference system. Now you have clients coming in, attaching to the system. And then the application can ask the platform, okay, I have this client here coming with this IP address. Which is the closest data center to this cloud, to this client? Or give me a location where I have presence within a certain latency from this client. This kind. On top of that, we have some higher order services, orchestration service, where you can specify all the infrastructure that you would like to have. That could be all the compute resources, storage, networking, and so on, as one bundle. And you create that everything and get everything. Instead of specifying one by one, give me this server connected to this network. Here you can specify everything at once. The SLA service here is even a higher thing. Here we can have templates of different kind of applications. And a tenant can specify that, okay, I need to be able to store this amount of video. I need to have high availability. I need to have backup for certain things. And that service will then translate that into the necessary resources that you need to have for this particular kind of application. And it will also create how this application should be able to scale in order to fulfill all these SLA parameters. So it will do that automatically. The architecture is, as I said, fully plug-in based. There's a small core of functionality. The rest, almost everything else, is plugins that we can change. I said it's a research platform. That means that we would like to be able to change functionality in it, in the system, in the platform. And we can do that easily by just changing different plugins. Another good thing when we design this kind of system is that you should be able for application developers to use the same APIs that we can do. If we have the need for a certain API, because it will simplify our task, it might be that same API might simplify the task for others. So that we have also made almost all the APIs in such a way. So I will now go into some of these. I will not talk about all of the services, but some of them. So you can see in more detail here. So first, compute and network services. Some few things about that. Okay, compute service. That will be the same as you will see in any cloud that you have. Okay, you want to have some virtual machine, some container, what it will be. But what we have done here is we have extended with the concept of location, because that becomes very important now. You want to have this compute resource somewhere in this distributed cloud. So you want to place it maybe here in Stockholm, in USA, or wherever it is. So, and that is not just geographical location, as you see here, example of region, country, city, or particular data center in a particular rack or on a particular host. It's more things than that. So we have extended that to specify sort of within a certain latency range from some other entity, and so on. So it's more than just geographical location. Okay, now I'm going to talk about the networking part. We have made a model of how to do networking. And we want to make this very simple. And most of you know, when we are discussing network and you do, what do? You draw a line on a whiteboard or something, or a piece of paper. I say, this is my network I have. And then you attach things to this network. Say, yeah, this is how we do our things. And this is very simple, and everybody understands this. So what to do next? Yeah, this is very simple, and we draw it on a whiteboard. But if we add some context to this, it becomes way more complicated. If this is a layer 2 network and it's supposed to spread all over the world, this is not, we cannot make a physical connection between these easily. We have to do something else. So we have to add features to this to realize that. That could be that we create these local networks in the local data centers, connect between some tunneling, between some gateways between these data centers, configure everything, and then we can have a sort of a layer 2 network here. And this is things that you don't want to bother with if you're an application developer. You just want to say, oh, I have this simple network. Connect my devices to that. And the platform should take care of all this and make it happen. If we add a different context, like this is a layer 3 network, yeah, that would be, you would start immediately think, okay, we will have some firewalls here, we will have some maybe NATing, routers and so on. Some will be virtual, others will be physical, we need to configure them and so on. So, but still you would like to have all this as a very simple model that you can just tell, this is what I want to have, make it happen. So that's part of this network service. Okay, now we have a distributed cloud, we have compute resource, a network and storage resource. In an ordinary data center, this is quite easy because you can have them all in separate and talk about them. In the distributed cloud, this becomes a problem because you might have computational resources in a data center if it's a small one, but you have no networking to that place, or you don't have enough storage and so on. So how do we deal with that? In a normal data center, it's easy. We can have a compute service and a network service. They can be totally more or less independent of each other because we are the basic assumption is that you will have networking to all the service within the data center. It's sort of connected in a full mesh, and you can have connectivity, and there will be enough bandwidth available. Of course, that is not entirely true, but that's the model we have. And that means that we can implement the compute service independent of the network service. And that is normal what you do in modularization of things. In the distributed cloud, in this case, we cannot do that because we have to try to allocate resources as one thing. So we make sure that we have this one thing. The way we solve this here is that we have separated resource allocation or placement from the rest of the resource management. So we have a resource manager that is owning all the resources. So the cloud or the compute service doesn't own the virtual machine resources. And similar with networking. So the compute service has to ask, when someone comes in and asks, okay, I want to create this virtual machine. It will then ask the resource manager, okay, can you allocate the virtual machine for me? And it will do that, but it will not create it. It will not do anything at that particular data center. It will just say, okay, you will have this resource. Similar to sort of an analogy you can think of is malloc and free in a C runtime environment. You request for a memory block, and you get that from malloc, and then you do something with it. Here, okay, of course, you can do that with your allocated machine, but it's not sort of created here. It will be created once it's assigned. This means that we can have a resource manager now that can allocate for an entire everything, networking, storage, compute, at the same time. Look at that problem at the same time. I will come back to that a little later. So we can say, okay, we can grant this. You can get all these 1,000 machines and all this networking you would like to have, or you will not. Okay, the container service, just a few things about that. It's something where you can specify sort of all the resources you like to have. It's fully parameterized. You can have defined temporal orderings so that you can say, oh, I need to create these things first. Once these servers are created, you can create this set of servers and so on. You can specify how the entire system should scale in different situations. Should we create more workers here or remove workers and so on. And we can specify how all these should be put together. And a very, very simple example could be that you define a number of servers, and they can, here we can see that you can specify some kind of location for them, where it should be. And then you just in network say, okay, connect these machines to this particular network. And we can have arbitrary complex specification of this one. Okay, let's press to that. Scaling service. This is scaling service is a little bit more advanced, what you normally find like in Amazon, where you only can specify that you want to have a certain number of more VMs when certain conditions happen, or remove someone. Here it's based on a set of rules, and a rule is a template for how things should be done when you need to increase the number of resources for a particular application. That could be horizontally, where you need to create more VMs, or you can increase the amount of memory that a certain VM gets, or more network capacity and so on. You can specify sort of limitation, minimal and maximum amount of resources that are allowed for this application. And the application will have full control about the activation of the rules. You can use API calls to this service and say, okay, now I want to scale out. Now I want to scale in. I want to remove something. You can also have it automatically done by the platform, specifying certain metrics. What should be measured? Should it be the network capacity or the bandwidth used, or some other things? So, and we have then a set of use cases. I will just briefly go in. So, if you don't specify any scaling, no scaling will be done at all. You can have full application control scaling, so that the application measures and decides when to scale. Or you can have fully automatic. You tell the platform exactly under which conditions they should meet. It will monitor and trigger once some limits are hit. It will automatically start this scaling. Or you can have some combination in between. An example on this where you can have a combination is that take this, I mentioned this video conference system before. It's easy to measure when you need to have more resources. You have a set of sort of video transcoding servers and so on. And you can measure the load on this. And if certain load exceeds certain load, you will add more media servers or transcoders and so on. But it's very hard to understand when can I remove a server, because with today's technology we're encoding and so on, you don't know. Nothing is sent over a link if no one is speaking. But the session can still be on, just that the participant in that conference is quiet. So you minimize bandwidth that way. And if we start measuring on the bandwidth, we don't know if it still exists or not. But the application knows that this session is still going on. So it can decide, oh, now they have disconnected, and then we can remove them. So it's easier to measure some. Sometimes the platform can do the work, sometimes the application has to do the work. And actually in the system, the automatic part, when the platform's doing, it's using exactly the same APIs as the application would do to initiate this scaling. So scaling rule, this is sort of JSON. It's fully parameterized again, so you can send initials to the initial things that instances that you create. You can say, oh, they should have this location and so on. We can specify too close these buttons. You can specify sort of this is horizontal scaling, this is vertical scaling, if you know. This is vertical scaling, then you increase the amount of resources of existing instance have. The other is when you create more workers or so on. You can specify very advanced on how to specify triggers with metrics you want to use. And you can specify, if you don't measure just on the workers, you can measure on a lot of different aspects of this. You can notify here which instances have you created or removed. That could be to a load balancer and so on. Get notified this. I have created these new instances. But the most interesting is the template describes what kind of instance should you create. And it's not only that you can specify that you can create a new server, a new VM. You can here set all collections of different instances. So you can specify different kinds of servers or things that you would like to have in one template. And even more, you can specify that a template could be a scaling rule itself. And we have used this in order to have a system where you can, again, I will come back to this video conference system. You want to set up now to scale out with setting up an entire cluster of things that should be placed in a certain data center, because you getting clients connecting very close to that data center. But you want it to automatically be able to scale out and in at that place. Let the platform do that, but the application decides where we should place this cluster, and so on. So then it will create, and using parameters, say, okay, create this cluster at this particular data center or location, and it will do so. And then at that site, it will run automatically and increase the number of resources the more clients coming in, without the application needing to do anything. Okay, again, we have a distributed system. So we have to, in all clouds, you have some kind of image service. You need to upload your image that should be run in your virtual machine, the code they should be running. In a data center, this is easy. You just have one place to put it. But in a distributed cloud, it's very important that the image that you need is there at the time when it's needed. And an image can be quite large. So we have a distributed image service here called Dawn, where you can upload an image to a central place, and that will then tell, so you upload it, it will look at it, it will chunk it up in different pieces so it can see, oh, this contains the same pieces, and then you can see that other images share the same parts. And once you have uploaded and sort of split this and said, okay, this chunk is one part that is common to a lot of images, it can notify all the instances, all the data centers that you have. Now this image is available. Now you can have different schemes for who should get this. Everyone, or just a few ones, or you can specify more intelligently, okay, now it's going to come to this particular data center. We are going to start up a VM here. You better get this. But having this, once it's notified, we can start using a peer-to-peer technology to distribute all these chunks, and they will only fetch the ones they need. And they will also, the different agents out in the different data centers, they will also transform these into what's needed at that particular data center with the particular cloud stack that are needed, how they want to have images. It will do that automatically. So now, going to the implementation of this. So we'll take a closer look how we implemented this. For the different services, we look at that. Normally, most of this, it's about some 100+ K lines of code, this system. About 75 to 80% is written in Erlang. This doesn't start out where we are using, of course, all this OTP stuff that you have, where the gen servers and applications and so on. But we didn't start out like that. From beginning, it was just a proof of concept prototype. And as it grow more and more of the components will be reused and so on. And then we started to adding, using all these OTP components and so on. So, of course, you can gain a lot from that, and we have gained a lot for making all things more usable for others. But for myself, I normally, when I do something, I do it directly, just using Erlang, because it's sort of, I can focus just on the problems at hand. And the rest is more that when you want to have it as a production system. Now this has turned into more, instead of a proof of concept, it's an experimental platform that we're using. That means that we need to have it more sort of streamlined. So looking at a particular service here, I will have a look at the compute service because it's sort of, it shares the common pattern. And what you see here is now sort of a map of what is going on inside Erlang. What process do we have? What modules exist in this? And so this is not a sort of an architecture. You will not see any supervisors in this part. So we see a lot of sort of things here. This one again. So the round ones is processes. We have some modules that will be thing. We have some plugins that we can see. So these are represented. These, of course, implement as Erlang modules. Now, if we start looking at this, it doesn't. Can you see this? That it's actually shaded around. So I have to point this. These here, this is sort of the Northbound interface. Looks really, you see it on screen. Well, anyhow, the yellow, what looks green-yellow here is third-party components. We're using yours as a web service here. And what happens when you get a request from the tenant, yours will receive that, will assign a new worker, create a new worker, and then it will we have for the different Northbound APIs, it will coming on different ports, and it will then invoke the right sort of interface for that API. And it will do a lot of things. It will automatically decode it if it's JSON, XML, and so on. It will verify that it's authorized. This user that's sending this request is authorized to perform this operation. This is done in common code, so you don't have to write that yourself. It's already done. Then you have to translate from the external API into a canonical language, a language we are using internally in this. This makes it way simpler if you have a canonical language, because we can have different sort of front ends, and internally it looks completely different. So every service translates to the internal language. This has good and bad things with that. It sort of freezes what you can do internally, but it makes it way more easy to adapt from the external point of view. It will then, after translation, we dispatch to the correct resource handler, internal thing. Once the result come back, it will post-process that. That could be that it sort of, in different cases, in context, you will provide different results. So in sometimes when you create a virtual machine, you will get all the information about the machine. But if you just list all the machines you have, you get just very little information. And it will do that depending on the context you do. It will then also translate back from the canonical format to whatever external format the tenant is expecting to have it in. So, and in the service logic, it's also easy. It's a REST API, so you have the normal CRUD functionality: create, read, update, and delete. And you can, of course, have other functions in each API as well. But more or less, they should parse the contents. In Win, we do parse the contents from a serialized canonical form into some record format that we are using internally, perform the requested action, and then send back the result to the Northbound API. The next thing is, now let's see, here, that is the Southbound. It will be arranged so that it automatically sort of invokes the correct plugin. I will come back to this. So it will be invoking the right plugin for this, and it will then has to format the request to whoever the Southbound execution environment wants it. It will get back the result, parse that result, update the necessary object, so on. And a lot of these things are common for most of the services, so everything is wrapped up, so you can easily create a new service. For me, it can take from anything from just a day or two to a number of weeks, depending on the service logic that you need. So it can go really fast to implement new things. And the actual sort of services that you implement, well, I've said this, it's a plugin technology. They don't actually know what they're creating. So if you run and want to create with a compute service, it doesn't know how to create a VM. Instead, what it will do is will use the plugin manager to learn. So it will say, okay, use on whatever node we are going to use on a node. Okay, I want to use the compute service at that node, and I want to create a server. So find a plugin that is suitable for this node, for the compute service. And the plugin manager will find the right plugin and invoke that functionality, and that will create it. And this here we pass the necessary information needed to create this. And I haven't talked anything about identity thing here. The first line here is just to create a local token. This is how we sort of the Win system authorizes towards that particular data center. So it will get an authorization token, so we can verify we are allowed to do this. Okay, plugins. It's a sort of simple behavior. It has two main callback functions, load and unload module. We can load them sort of, or every function that you define in the API, external API has to take sort of a state variable, and the rest what is needed. We can specify if the plugin should be loaded at start when you start up the system or when first use. And then we have functionality here later in the plugin manager for finding the right plugin, so on. It's built on levels, so we have a general basic plugin manager. It's thread safe. By that I mean everything of the actual code where you run in this function in the plugin is not run in the plugin manager. It's run in the thread that was, or a process that was calling this. So if you want more complex ways to find the right plugin, then we see, as I was using this wind plugin manager that is based on location. So here we can specify sort of the node, the name, a function, or a type for a different node. If you have two nodes, specify two node and type, it will find the best fit of the technology. This we are using, for instance, if you want to set up a tunnel for networking, connecting two layer 2 networks, it will find the technology that fits both data centers. So we'll try to find the best fit for that. So on. We also have a driver management for singleton plugins that could be like a driver for a database, something that you will not depend on the particular data center you're using. It's more for the system itself. So you can have drivers. Okay, another thing we wrote for this was what we call evirt. It's an Erlang API to libvirt. It's a fully one-to-one mapping. At the time when I did this, it was 280 plus functions. So it supports libvirt 0.9.3. Now I think it's up 1.2.9, so it's lagging behind. It has full support for callback functions. libvirt are using a lot of callback functions where you register function C functions that it will call. It's based on another module called ASPD. So let's go. It's a asynchronous synchronous port driver. So it's based on Erlang ports, but it simplifies bridging for libraries between Erlang and C or C to Erlang. It's very simple to use. It supports, as I said, there's you get with support for callback functions, and you can actually write a user or register a function, anonymous function, and to be called from the C code directly. It has a library of convenience macros for writing this code, so it makes it much more simple than the existing ones. And it has support for logging, so you can turn on logging on different sites to things. So another comment I have is for testing this. I based this, the testing is done using a unit test. Tests that are written in different level, they will test that level itself and all the code in the module you're doing. But it will also test all the levels that are involved below. And as I said, it's a plugin based thing. That is that if we are using HTTP client that the system sees, and we have an HTTP client that emulates entire OpenStack cloud of arbitrary size. And so in normal mode, it will call iBrowse to do the request, and then it will send out that, however that's sent out. But Wind doesn't know. In test mode, it will just plug in the emulator instead. So it looks like we have an entire huge distributed cloud, a lot of data centers. And Wind, the rest of the system, doesn't even know if it's running in test mode or against the real cloud. So everything up to this point is tested when you run this. So it's a simple technique to test everything. Another reflection, a final reflection before closing is in Erlang, it's very easy to use as processes are cheap. It's very easy to just use processes everywhere. In Wind, we have carefully been thinking what processes are actually needed. And most of the code handling a request will be run in the process that was created, or the worker, from yours. And we will just do small side to the different other internal functionality, like the resource manager or plugin manager. Very short things to find out the rest of the database. And most of these calls are very short as well. So that means that we have less serialized, less things. And having that you don't use too many processes will also help you not getting deadlocks. So, okay. What are we working with now? Yeah, this was done a couple of years ago, but it's sort of half active anyhow. I'm currently working on a fully distributed scheduler where you can schedule over this huge distributed cloud, very efficient, not having a central database, having knowledge of all available resources, it's fully local. Working on a policy description language where you can describe what you would like to have and all the SLAs that should be provided, and an engine for that can automatically sort of do what you would like to have. So this is a sort of a prologue approach over servers that you put on top of this. And I'm also working on what I call e-flows. It's a completely new behavior. It will look like the other behaviors, but it's for having a set of tasks where it could be create network, create servers and so on, and into flows that could then will be the entire flow will either be accepted or it will be rejected. Okay, so questions?
I've got a question about your scheduler. Do you have something for dynamical load balancing? For example, in vSphere, there is a mechanism called DRS, dynamic resource sharing. And also, the next question, do you have some mechanism for HA?
Okay, regarding scheduling, the entire scheduler is a plugin. So we can put in different schedulers, testing that. So we are testing different schedulers. And we have research going on where we're testing different things. The one that we have been using, this system has been shown for a number of times at Mobile World Congress. And we have used a very simple scheduler. But there work going on for exactly this kind of schedulers that you were talking about. Regarding HA, we have another research project working on exactly that. It's done in Montreal. So we have quite advanced things on that. It's not built into to Wind, but yes, we are working on such things.
Have you considered the pricing model of different clouds and how to take that into account in your provisioning?
Yes, we did a project like 1.5 years ago to do that exactly that. It's not built into this sort of, but it was based on the same sort of assumption and separate service for actually doing this kind of thing. But we haven't integrated into the platform. But yes, we have done that.
Okay. Is it open source or are you planning to open source
Yes. And one colleague, you will get this question, and I didn't mention. No, it's not open source yet. I hope to be able to do that. I haven't even been allowed to talk about this before. So this that I can talk about it is quite nice. Some of this, like EVIRT and the lower things that sort of support things that is no business logic, I hope to be able to release as open source. The others, that might be the way to get them really accepted, is that you put it out to a startup And then the Ericsson will buy back that startup. So I cannot promise anything because it's not up to me. Some parts I really try to get in open source. So that is my goal because I want to bring back to the community.
Okay, thank you for the questions and thank you, Joacim, again.
Yeah.